systems of two equations and two variables by graphing. And we talked about solving systems of two equations or systems of inequalities in two variables, also by graphing. And I think I assigned like 1 through 8 or something. Do you guys have any questions on 1 through 8 that you want to talk about before we start in on the next stuff?
What's free cash flow?
Okay, fair enough. That tells me what I needed to know. Either we haven't done it yet or we are good with whatever we did. So that's fine. So, what we're going to talk about next then is we're going to talk about solving these linear systems algebraically. So instead of graphing, we're going to do this algebraically. What's one of the big drawbacks with graphing, or some of the drawbacks of trying to solve these systems by graphing?
You gotta do it.
What's up? No, go ahead.
I was gonna say you gotta write it yourself.
Yeah, so if you have to write it yourself, what does that mean?
It could be inaccurate.
Neatness counts, right? Like, if I'm supposed to be picking out the coordinate point from my drawing, what if the solution was like 1.03 comma 7.56?
You can achieve that yourself.
It's going to be pretty rough. You're going to need an awfully accurate drawing, like where you have, like a graph paper where, like going by 0.01s is like one tick mark on your graph paper, which is like woof trying to do that, right? So we would like a better way, because if you run into something that's a decimal like that, like good luck trying to get that to shake out of a picture. So we're going to talk about two algebraic methods today. The first one is called substitution. Let's zoom out a little bit now. So for the substitution method, you can choose to start with either of the two equations. It does not matter which one you start with. And you're going to solve that one equation in terms of one variable. So you're going to either get the x by itself or the y by itself. It does not matter which one. That's step one. Step two, using that new equation that you've just gotten that starts either x equals or y equals, you're going to substitute that into the second equation. That new equation now has only one kind of variable in it, either x or y, depending on what you substituted in. And now you can solve algebraically because you just have one variable. Now it's just like a normal Algebra 1 problem. So let's take a look at this example here. So I have the system 2x plus 5 equals negative 5, and x plus 3 is equal to 3. So it doesn't matter which equation you use and which variable you want to try to isolate, but you can certainly make your life much easier by choosing wisely here. My goal when choosing is I don't want to have any fractions. Okay? So my goal when I'm doing this is I want a problem where getting a variable by itself, I don't have to do any dividing. Or if I do have to do any dividing, the division isn't going to result in a fraction. Everybody's okay with that? So if I look at my two equations and the two variables within each equation, which equation would I want to pick and what variable from that equation would I want to isolate? Great. So Nathan says, let's do equation 2, and we're going to get the x by itself. Again, the reason I would do that, I think that is the best choice, is that I'm able to get the x by itself without having to do any division. And as a result, I'm going to generate no fractions. So to get the x by itself, all I have to do is subtract 3y from both sides. And I'll call that equation 3. Everybody's cool with that? Now what I'm going to do is I'm going to take my result from equation 3 and plug it into the x in equation 1. So I'm going to take 3 and plug it into 1. So I still have the 2, and I still have the plus 5y, and that all still equals negative 5. But in place of the x, what am I going to plug in? 3 minus 3y. So notice now the equation I'm left with has only y's in it. Excellent. This should be easy for us to deal with. I'm going to start just by distributing through the 2. I'm going to combine my like terms. So negative 6y plus 5y is negative y. I'll subtract 6 from both sides. And then divide both sides by negative 1. Everybody's okay with that? So that's my solution for y. To get my solution for x, what should I do? Yeah, I'm going to plug that back into my equation 3. It doesn't really matter which equation you plug it into, but equation 3 already has the x by itself. So like, there's no algebra to do. I just have to do some simplifying. So I'd write my final answer as the ordered pair, negative 30, comma 11. Now, quick question. So this is an example where I get exactly one solution, right? What are the other two possible outcomes I can have?
2 and 0.
Not two solutions.
Are the same.
Infinitely many,
Yeah.
and then no solution, right? Yes.
Where did you get that from?
So I'm talking about equation 3
Oh, okay.
that I labeled here. So I'm plugging that answer 11 into equation 3.
Okay.
You see that? Okay. So what happens, or what does no solution or infinitely many solutions look like? So at step 2, after you've made your substitution, your equation is going to simplify to something like 0 equals 1. Some statement that's not true. So all your variables will kind of eliminate, and you're left with some contradictory statement that's never true. So this is for the no solution situation. I should say, put it here. Maybe I'll use a different color also. So in an infinitely many solution situation, actually, let's do it here. That would be less writing for everybody. For an infinitely many solution situation, you'll get something like 0 equals 0. Some statement that's always true. 1 equals 1, 7 equals 7, 5 equals 5. -3 equals -3. Something that's always true. That's going to be our indicator that we have infinitely many solutions. So just as an aside, we'll come back and circle back and do some more answers with that, but it's the same idea. Our second algebraic method is called elimination. So let's look at what that looks like. So in step 1, we can multiply one or both of the equations by a constant. It does not need to be the same constant for both equations. So I can multiply equation 1 by 2 and equation 2 by 3. That's fine. They can be different constants. The goal in doing that is so that one of our two variables has opposite coefficients. So I want, say I'm wanting to eliminate the x's. After I've done multiplying by my constants, I'd want one equation to be 2x and the other equation to be -2x, right? Once I've done that, I'm going to add my two equations straight down. So I'm going to add the left sides together and we'll add the right sides together. And the result should be a third equation in one variable. That's step 2. I'll solve that equation for the remaining variable and then plug my answer back in to a previous equation to complete the problem, to solve for the second variable. So let's take a look at this example 11. So equation 1 is 3x minus 7y equals 10. And equation 2 is 6x minus 8y is equal to 8. So again, it doesn't matter which variable we try to eliminate first, whether we want to try to eliminate x or eliminate y. But just like substitution, choosing wisely can reduce your workload. My suggestion to you is try to do it the easiest way possible. So if I look at x's and I look at the y's, I'm looking for a situation, can I multiply just one of the equations to make the variable coefficients opposites? If so, that's the one that I'd like to use. Or even if I don't have to do any multiplication at all, sometimes that's possible. That's what I'd like to do. But basically, I want to multiply by as few constants as possible. So with that in mind, should I do x's or y's? Yeah, I agree. I would eliminate x's first. And what do I need to do to eliminate x's first? Yeah, very good. So I'm going to actually call these equation A and B so that the numbers doesn't get so confusing. So we're going to do -2 times equation A, and then we're going to add that to equation B. Everybody's okay with my notation as like what I'm describing that I'm about to do? So -2 times A is -6x plus 14y equals -20. Right, I've just multiplied everything in the equation by -2. B is staying the same, so I have 6x minus 8y is equal to 8. And I'm just going to add straight down. So that gives me 0 plus 6y equals -12. Or just 6y equals -12. Well, that equation's easy to solve for. I just divide by 6. There's my answer for y. Now that I've accomplished that, I'm going to go ahead and plug that answer back into either equation A or equation B, it does not matter which, and solve for the x. Looking at our two equations, is one of those going to be any easier to plug into than the other? I think they look about the same to me too. So I'll do equation A for alphabetical reasons. So I'll just plug that into A, which gives me 3x minus 7 times -2 equals 10. Right? That was, okay, good. So 3x plus 14 equals 10. I'll subtract 14 from both sides. And then divide both sides by 3. So my answer would be -4/3, -2. Note that that one would have been kind of rough to come up with by graphing, right? Yeah. Finding a -4/3 would have been tough to be so careful and so accurate that you get that to come out correctly. Okay. Let's look at another example here. This one will be a story problem, though. What's going to be the hard part about the story problems? Is you're going to have to write your own system, right? So let's read our story problem here. It says, to raise money for new football uniforms, you decide to sell t-shirts. Short sleeve t-shirts cost $5 each and can be sold for $8. Long sleeve t-shirts cost $7 each and can be sold for $12. At the end of the fundraiser, you determine that you spent a total of $2,500 to buy t-shirts, but sold all of them for a total of $4,200. How many short sleeve t-shirts did you sell? So let's start by identifying what our variables are and what they're going to represent. So what two things do we not know? Okay, great. So I'm going to use S to equal the number of short sleeve t-shirts. And it doesn't matter whether these are bought or sold because I know that I sold all the t-shirts that I bought, right? Yeah. So I can just say in general. And I use L as the number of long sleeve t-shirts. Everybody's good with that? And then I'm given a bunch of numbers in this problem. Let's look at what each of these numbers is representing. So what is the $5 representing? The cost of a short sleeve t-shirt. Let's say the cost per short sleeve t-shirt. Okay. And then the $8, what is that? Yeah, so I'll call that the price per short sleeve. Shorf sleeve? What is a shorf sleeve? Yeah. T-shirt. Whatever it is, I'm not buying it. Okay. The $7 is then the
Cost per long sleeve.
mm-hmm. And the $12 is the okay. And the 2,500 is
The total cost.
total cost of all t-shirts. And the 4,200 is the
Price.
total profit, we'll say, of all t-shirts. Okay. So since these guys are totals, what can I say about them? I'll have my two equations, equation A and equation B. Yeah, those will be the solutions to my two equations, right? Everybody feel okay with that since they're totals? Sure. Okay. How did I get the 2,500?
Gave it to us.
No. But like, what things did I have to add up to get that total?
The cost of the short sleeve.
Okay, so how much did I spend on short sleeve t-shirts?
5S.
$5 times each short sleeve t-shirt, right? And then how much did I spend on long sleeves?
7 times.
Good. And then how much did I bring in from selling my short sleeve t-shirts?
8 times. 12.
Yeah. Does everybody feel okay with how I built this system out? That's typically the hardest part because as we saw with both the substitution and elimination, these were not terribly difficult procedures, nor are they unfamiliar, right? These are things we've done a couple of times now. All right. So which variable is it going to be easier to eliminate? Yeah, they look about the same to me, right? All right, so what do I need to do to equations A and B so that I can eliminate the S's? What should I multiply equation A by? 8, okay. And then what do I multiply equation B by? Close.
Negative.
One of them has to be negative, right? Does it matter which one we make negative?
No.
I'm just going to do it the first one so it's less confusing to have plus a negative when I wrote it down. But there's no good reason why I made the first one negative. It could have been either. It does not matter. All right. So negative 8a is going to be negative 40s plus, well, let's just write minus 56l is equal to 10,000, negative 10,000, I think. No, 20,000. Right? 4 times 25 is 100.
Yeah.
And we did that twice because it's times 8. All right. You should use your calculator, though. There's no reason not to. The equation 5b then is going to be 40s plus 60l is equal to 21,000. So then we'll add down. That can't be right. Oh yeah, because I multiplied by 5. Yeah, okay, fine. So what do I end up? I end up with 4L is equal to 1,000. So if I divide by 4, L is 250. And then let's put a unit on there. So those are long sleeve t-shirts. And then to get S, plug it back in. Does it matter where I plug it into?
No.
No, man. I'll plug it into equation A. So that's going to give me 5S plus 7 times 250 equals, what was it? Thank you. Okay. 8 times 250 is going to be 2,000, so that's going to be 1,750 then. Again, use your calculator. I'll subtract 1,750 from both sides. That's going to be 750. And 750 divided by 5 is 150. Everybody feel good there? Again, the most difficult part is the setup, right? If you can get the equation written, should be a piece of cake. The format of this story problem is super duper common, where you're given like 4 rates and then 2 totals, where your variables are quantities. Because I know rate times quantity gives me total, right? So that's a very, very common setup for this kind of solving a system story problem. I'd be shocked if you did not see one question like this on like an ACT, or one question formatted such as this on an ACT if you took an ACT recently. This one should sound pretty familiar. I think they almost always have a story problem involving a system.
I had ACT tutoring yesterday, and we did like a problem with that.
Yeah, super common ACT question. All right, couple more examples here.
So you have to do like
Okay. This one says solve the system using any method. All these systems could be done either with substitution or elimination. Which one do you feel is most appropriate here? I would say because of this, either substitution or elimination is a good choice. Neither is going to prove to be terribly difficult. Everybody happy with that? So say you want to do it as a substitution problem. You don't have to do it that way, but maybe you said, oh, I see a coefficient of 1. That seems tailor-made for substitution. So now that we have this, we'll just plug it into the second equation. So I distribute this through. 6y plus negative 6y just cancels out. I have 12 is equal to 8. That means no solution. Now notice that I could have noticed that from the jump, without even trying to solve this system, that this is going to have no solution. To go from x to 3x, I multiply by 3. To go from 2 to 6, I multiply by 3. But to go from 2 to 4, I'd have to multiply by, or from 4 to 8, I'd have to multiply by 2. Because this one is different, that the left-hand side is a factor of 3, but the right-hand side is a factor of 2. That tells me right away that this is going to be elimination. I could notice that without actually having to do the problem. Now, chances are you wouldn't notice that in a test setting. But if you did, you can make that claim, what I did right there, and just say no solution, be done. That is sufficient conditions to say no solution if you're able to do notice that. And boy, that saved a lot of work. Yeah. But you don't have to do it that way. But we talked about that last time, so it's worth bringing up again. Let's do this one. So again, we're told any method. What's your preference? Well, I don't like substitution at all, because no matter what variable I try to solve for, I'm going to end up with a fraction somewhere, right? So I would do elimination here. Because elimination is kind of the same whether things work out or not. In general, I like elimination more than substitution. But substitution has its benefits when it's easy, because it's usually really easy. The nice part about elimination is it really never gets crummy. All right. So let's pick a variable. Which variable do we want to eliminate? X. Okay. To eliminate x, what do we need to do?
Top by 7 and bottom by 2.
Great. Am I out of time here, guys?
Yeah.
Okay. Go ahead. We'll finish this one up when we get back. All right. So we left off example 14. We're solving this system. We decided elimination was the way to go. Decided that between the x's and y's, it was like 6 of one, half dozen of the other, about the same. So we decided to cancel the x's. So to do that, we multiplied equation A by 7 and equation B by 2. Why is neither of those numbers negative?
Because the 14, we're trying to take an extra 14.
Yeah, one of the coefficients is already negative, so we don't have to worry about that. Great. Okay, so my equation 7a is going to be 28x minus 70y is equal to 56. And my 2b is negative 28x plus 70y equals negative 56. When I add these down, I end up with 0x's plus 0y's equals 0. Or just 0 equals 0. Yeah. So when we say infinitely many solutions, does this mean that all ordered pairs x and y are a solution?
No.
No, right? So one thing that we might like to do for our infinitely many solutions is to describe the form of those solutions. So remember how we plot points and we plot like x comma y? That's the same as like x comma f of x, right? Everybody agree with that? So if I take one of these two equations, say equation A, let's put 8 back to, yeah. And I wanted to say get the get the y by itself. And then I'll divide both sides by negative 10. What that allows me to say then is that each of my solutions will be in the form of x comma yeah, x comma 2/5 x minus 4/5. So what this is really saying then is like this is giving me a form of how I can generate those infinitely many solutions. So like if I pick x to be 0, then y would be like negative 4/5. Right? Or if x is 1, then y would be negative 2/5. And since I have infinitely many choices for x, I'm going to have infinitely many unique points. So this is a way to kind of write that general form for my infinitely many solutions. Everybody's okay with that? Now, did I have to arrange it this way? Could have I instead taken 4x minus 10y equals 8 and decided to get the x by itself? Sure, I could have done that. If I do that, then I would replace the x with 5/4 y plus 2 and then y. So here I'd be picking values for y, and those would generate the x coordinate. And again, that's in one of, since there's infinitely many choices for y, I have infinitely many points, and there we go. And conceivably, if I picked, like this value for y, I would get that x back, right? Is everybody okay with that notion? Now that's really easy to do when we have two equations, which is why I wanted to show it to you now, because when we have three equations and I ask you to do that, it's a little bit tougher, just from a like keeping track of the symbols all going around. But it's still okay. But either of these would be considered reasonable solutions. How do you guys feel about substitution, elimination in two variables?
Good.
Is this familiar? You guys remember doing this?
Yeah.
Do you feel like you're pretty good at this already? Okay. So what have we assigned for this stuff? Would have done 9 through 18 would have been the problems that go with that section. And then since we feel good about this, let's talk a little bit about the next section today, and we'll do some more next time as well. Oops, that's not the button I want to press. Okay. So in section 4, we're going to be talking about solving systems in 3 equations. So we have 3 variables, so we're going to need 3 equations. So what does it mean to have an equation in 3 variables? Well, you're just talking about some kind of equation in the form that can be written in the form ax plus by plus cz is equal to d, where the a, b, and c are not all 0 at the same time. So what does it mean to be a solution for a system of equations in 3 variables? What's that solution going to look like? Well, it's going to be a ordered triple, like an XYZ, that satisfies all the equations. Geometrically, that's the point where the 3 equations would intersect. So let's think about geometrically what that's going to look like. So if I have an equation x or ax plus by plus cz is equal to d, that's got 3 variables in it, so it's going to be an equation in 3 dimensions, right? So instead of having an xy plane, we have an xyz plane, except it's not a plane anymore. It's like it's 3-dimensional. It's like it's being like inside of a fish tank or something, right? A big rectangle. Everybody's okay with that? So what does the graph of an ax plus by plus cz equal d look like? So if we think about 2 variables, our 2-variable space we're graphing in was a plane, and we get a 1-dimensional object, which is a line. If we have a 3-dimensional space we're graphing in, we're going to get a 2-dimensional object, which is a plane. So the graph of the equation ax plus by plus cz is equal to d gives us a plane. So one solution, or a solution to our system, is going to be the intersection of 3 planes. Planes. Well, let's think about geometrically, visually, kind of what that would look like. It looks something like this, where I have 3 planes there. I colored them each a different color, but they're still meeting at that exactly one point there. The black dot is the only place where all 3 of those planes meet at the same time. What is infinitely many solutions going to look like? Well, it could be just one plane, but it doesn't need to be just one plane. It could look like, more generally, it could look like this, where the 3 planes intersect, but the thing that they form is a line, right? Where one of the coordinates is fixed, but the other two are not. And then what is it going to look like if we have no solution? Well, it has to be a situation where there's no place that all three planes intersect. There's actually three different pictures that could kind of happen. You could have where each plane intersects the other two, but you never have a place where all three of them meet. You can have a situation where one plane intersects the other two, but again, no place where they all meet. Or you can have a situation that's the most obvious where all three planes are parallel and there's no intersection at all. So I'm just trying to give you like a three-dimensional picture of kind of what we're doing. Are we going to do anything graphing three-dimensionally to do this? No. We're going to do it all algebraically because plotting these things is a hassle. We can do it. You can do it in a two-dimensional space. It's not that bad, but it's a hassle. If you look even at your draw options, oh, they used to have it here. That's not what I wanted. No. Huh. They updated and they lost the thing that I like to use. It's a bummer. Oh, shapes probably. There it is. So if you look under, even in your OneNote, if you look under shapes and then graphs, no, that put it someplace I didn't want it. It gives you this, and this is like what a three-dimensional axis would look like. So the way to look at this is you have like a straight vertical and a straight horizontal. Those are in the sheet of, like in your sheet of paper. And this one on diagonal, you want to look at it as if it's like sticking out of the piece of paper at you, is the way to visualize that. And you can actually plot points and stuff on there, but it's like, it's a hassle to do it. Let me be frank. And beyond the scope of what I'd ask you to do in a class like this. If you're in the honors class, we would do that. But we're not. All right. So to solve one of these three variable systems algebraically, we're going to use either substitution or elimination. Now, what's the difference between a two-variable substitution and a three-variable substitution?
You got one more step.
You have one more set of substitutions to do. That's exactly right. So you're going to pick one of the three equations, solve that equation, or get one of the variables by itself in that first equation. Doesn't matter which equation you pick. Doesn't matter which variable you get by itself. You'll then take that and substitute it into the other two equations. Simplify down, so now you'll have two equations in two variables. And then you repeat the process like it was a two-variable problem. So it's just a little bit of extra. Let's do a quick example here so you guys can see that. Okay, so this one, again, these three variable ones get a little bit messier, so try to give me your best attention here. I know it's late in the day or late in the class. So of these three equations, we can pick any one, And then of the three variables, x, y, and z, we can pick any variable in that equation to isolate. Which equation, which variable would be the easiest one to pick? We're doing substitution here. So I would agree. I'd pick equation 3, and I'd be getting the y by itself. Because again, when we're doing substitution, the goal is no fractions. So if I don't have to divide by a real, like a whole number, or something other than 1 or -1, I knew that I'm not going to get any fractions if I didn't have any to start with. So that sounds good to me. So we'll start by subtracting over the 6x, subtracting over the 4z, and then we'll divide by the -1. To get that. Now that we have this expression for y, I'm going to go back to the old system, the original system, take the other two equations, and substitute that in for the y's. So equation 1, well, I'll call it, and again, I'm going to call these A, B, and C. We're going to have 4x plus 2, but then instead of y, I'm going to write 6x plus 4z plus 1. And then equation B, I'm going to have 2x minus 3y, but instead of the y, I'm going to write 6x plus 4z plus 1. And now we got to distribute everything through. And do the same thing down here. Remember to take your negative with you when you're distributing things through. So if I combine my like terms now, I have 4x and 12x, that becomes 16x. I have 8z and 3z, that becomes 11z. I have 2x and -18x, that becomes -16x. I have -12z and positive 5z, that becomes -7z. Oops. I still have that -3 equals -14. And then I'm just going to subtract that 2 over. And then in the second equation, I'm going to add the negative, or I'm going to add 3 over. And this is my new system that I'm going to solve. What method do you want to use to solve this system? Substitution or elimination? Yeah. If I look at it, this is screaming at me. Please use elimination on me. Why? I have a 16x and a -16x. The coefficients are already opposite. In general, elimination is going to be your better bet here. And if I divide both sides by 4, I get my answer for z. So now to get my answer for x, I'm going to plug back into one of these two variable equations, it doesn't matter which one. I'll just use the first one. So add 33 to both sides and divide by x. I get x equals 2. And then what am I going to do from here? I'm going to use this equation to get my y. So I'm going to plug in my x and my z. I already forgot what that was. Y equals 6, and then x plus 4z plus 1, I think. If I do that, I get 12 minus 12 plus 1, so y equals 1. Taking that all together, there's my solution. Yuck-ers, right?
Yeah.
In general, Mr. Kulik, I ain't got no time for substitution. Like, that was a lot of mumbo-jumbo. Elimination typically works a little bit smoother. That would be my recommendation for all 3 variable problems. Unless it's like screaming at me where like already one of your variables has been isolated for you in advance. Am I going to mess around with substitution? So if I'm doing elimination, again, the procedure is basically the same. What I do is I pick one equation of the 3, it doesn't matter which one, to act as my eliminator equation, where I'm going to multiply that equation by some constant so that I can eliminate the same variable from the other 2. Okay? Go ahead and eliminate that, creates two variable equations, and I just do another elimination round. So it's basically the same process, but takes 2 steps, or 2 sets of eliminations. Let's say let's go ahead and use this example here. So we're going to solve this one with elimination. So first things first is I would pick a variable to eliminate first. X, Y, or Z. Do you think it matters? No, right? Is there one that's going to be easier than the other? In this case, I would say no, because in each situation, I have an X, Y, and Z that has a coefficient of 1. So that'll make the eliminations easy no matter which variable I choose to do first. For the sake of argument, let's do the Z's first. Okay, so if I look at equations, again, I'm going to call these A and B. If I look at equations A and B, what do I need to do to eliminate the Z's? Right, that'll eliminate the Z's. And then what do I need to do to eliminate the Z's from equations B and C? Everybody's okay with that? Notice that I can use a different constant for each elimination. That's fine. I do not have to use the same constant for both of them. And I could multiply equation A or C by something if I need to. That's fine. But in general, I try to do this so I don't have to do that, right? So we'll start here now. So I have equation A, which we didn't do anything to. And then we have 2 times equation B. And when we add down, we get 15x minus 3y equals 6. Now we have negative 3b, so it's 18x plus 6y minus 3z is equal to positive 6. And then equation C, we're not doing anything to. So just recopy that one. When we add down, we have negative 17z plus 10y equals 13. These now are going to form a new system of equations D and E. Oops. So we'll repeat the elimination process. Which variable does it look easier to eliminate, x or y? Seems about the same to me, right? But you want to eliminate y's? Let's do it. What do you want to eliminate the y's? What do we have to multiply equation D and E by respectively?
D by 10 and Y by.
Everybody agree? Okay. So 10D is going to be 150x minus 30y is equal to 60. And then 3e is going to be, what's that? Negative 51x plus 30y equals 39. If we add down, I get 99x equals 99. So divide both sides by 99, we get x equals 1. What do I do from there? Yeah, I'm going to plug it back into D or E. It doesn't really matter for the sake of argument. I'm going to plug it back into E because the division with the 10 there looks pretty easy to me. Okay. Bye, dude. Did you call him poop? Oh, poo. Not. Oh, pook? Oh. I thought you called him poop. I was like, oh, that's rude. So there's my value for y. How do I get z? Yeah, I send it all the way back to either A, B, or C, right? Does it matter which one? No, which one is Mr. Kulik going to pick, though? I'm going to pick B because the coefficient on z is 1, so I don't have to do any division. But it does not really matter. Scroll back so I can see where I was at. So my XYZ then is 1, 3, 2. Oh my goodness. Look what I did. I miscopied. That was a -2 there. Shucks is right. Hope you weren't using pen. Yeah. Well, at least all you had to do was sneak a negative sign in there, right? That's not so bad. If there's a place to make a mistake on the very last part is the place to make it, right?
Yes.
All right. I'm going to do one more example, and we're going to call her quits for today. Sound good?
Good.
No, I would not add that one.
All right. So let's say we have, well, am I almost out of time? Oh, why am I getting started on this? That's dumb. It'll take me at least 5 minutes to get through that. So we'll stop there then. You guys should try.
75. She actually loves it. I'm gonna be like, you should think. If the teacher asked me what I was doing, I was like, I don't even know what you're saying. I would probably throw my window. I mean,
Oh, really?
I would probably throw the notebook out the window.
Let's say 19 to 26.
Also, I didn't
No,
know
one.
how it was damage and I agree with you.